And are we still awake? Good. So, yesterday afternoon, Chris phoned me because he's staying at our house this evening. And he promised me that he would be on his way first thing this morning. And I had a bet with my wife. She lost. Chris turned up at 2 o'clock. Jane said he'd be here by 12:30. None of us thought he'd be here this morning. Anyway, Chris, please talk to us about monitoring networks using perfSONAR.
You will be pleased to know that some of these slides are right up to date with the latest results. It's the network. There's a problem with the network. How often have you heard that? And as working as my employer runs a network, we're kind of interested in working out whether it really is the network. And so we use perfSONAR to do that. So I'm going to cover JISC and the JANET network, and then I'm going to talk about perfSONAR and using it to measure bandwidth, latency, and also some performance tuning that you can test with it. So JISC runs the JANET network. Now, I guess those of you who've been to university in the UK know about the JANET network, but we cover not only universities, we cover FE colleges and research institutes and schools even. The backbone's 800 gig in places, will be upgraded to a terabit, and that's made of 100 gig links predominantly. And they're largely run over dark fibre, so we run an optical network over which we run connections, so we can potentially run additional things over the same dark fibres. And we're connected to educational networks worldwide via GÉANT. So we've got this really nice, rather fast network, and one of the things that we want to do is make sure that people are able to use it and use it well. So science communities, notably particle physics, move vast quantities of data. In a data challenge in the spring, the CERN experiments moved 110 petabytes worldwide in 2 weeks. So quite a lot of data. To do that, you need to follow science DMZ principles, or research data transfer zone principles. That's to say, if you've got a firewall that doesn't have very good performance, then trying to send hundreds of terabytes of data over it probably won't work. So you need to find an appropriate balance between security and performance, and perhaps putting your science cluster outside the corporate firewall, but appropriately firewalled and appropriate is the sort of thing you need to do. And the other thing that you find is that you need to do performance monitoring. And one of the tools that we use in that armory is perfSONAR. We've got a number of other tools, but just to give you a brief summary, we've got a 10 gig and perfSONAR node in Slough. We've got 100 gig in London. And we've got also iPerf and Ether. So if you want to test against those, let us know. Everything's both dual IPv4 and IPv6 dual stack, and they're connected at an MT of 9,000, so we can do jumbo frames. There's a link there to our performance test facilities webpage. So one of the things, if you've ever listened to a talk I've given before, you've probably seen this graph, but if you get even a tiny amount of packet loss, it has quite a significant effect on international data transfers. So if you see the latency going up from 0 to 100 milliseconds, that's roughly transatlantic. You'll see a 10 gig, you start off at 10 gig on the LAN, and you get a fraction of a gigabit over the wide area network. So we engineer our network to try and avoid that packet loss, but it's really quite critical that you do. So perfSONAR allows you to measure bandwidth, latency, one-way latency and packet loss. It can also do traceroute. And what we've got is a mesh of 10 sites that we're interested in. And actually they're a subset of the particle physics sites that are particularly keen on this sort of thing. perfSONAR has gone for a major upgrade, and so we're not yet covering them all. But you can see in green are the sites that are performing, the pairs of sites that are performing well. In red, in yellow are the sort of, it's a bit iffy. And in red, there looks like there's a problem. Now, one of those sites that's not performing well is our gigabit test node in Slough, our small test node, which is only connected to gigabit. And clearly, if you've only got a gigabit network card, you're not going to get more than a gigabit. Unless somebody's got some magic. There's test nodes worldwide. Particle physics uses that, and the square kilometre array, which is a radio telescope, is starting to play with these sorts of things. So what can you do? Well, this is a test from our node in London to a test at Rutherford Appleton Laboratory in Oxfordshire. And they've got 100 gig connectivity at the site. And what you can see is that from them to us, we're capable of achieving 30 odd gigabits single stream, which is pretty good. And that's limited by the kernel. I think it's CPU limited. So that's nice and steady in one direction. It's somewhat less steady in the other direction. Why is that? Well, we don't know, and it's one of the things on our list to investigate, but it's possibly the kernel. And actually, if you're really interested in top whack performance, you need the latest kernels. So Ubuntu 24 apparently has got about 40% better network performance at the top end than Scientific Linux Red Hat has. So TCP tuning is important, making sure that the buffers are big enough. And the other possible thing that might be causing a problem is somebody's actually transferred some real data. And so real traffic, I mean, it's terribly inconvenient when people actually want to transfer data over our network. It'd be nice to keep it nice and clean for testing. And a couple of other examples. So the top example I will call University A, where from our node in London to that university, we're getting 8 odd gigabits, and the two, the yellow and the green, are IPv4 and IPv6, so pretty good performance for both. Down at the bottom, at a fraction of that, is the transfers from them to us. So there's clearly a problem. What it is we haven't identified yet, but it's clear that there's a little bit of a problem. And so it pinpoints that there's a problem and there's the direction of that problem. The second example on the bottom is University B that has just received a 100 gigabit network upgrade. And you can see exactly where it achieved that network upgrade. It was roughly here. And what's happened, surprisingly, is that once it got the upgrade, instead of the performance hitting the 30 gigabits we're getting to Rutherford, it's gone to about 3, but it's much more stable. And again, that looks like there's a problem somewhere. What it is, we're not quite sure, and they got the upgrade on Tuesday, so that again is something we need to investigate. But it does indicate that even though you've got this really fast network connection, there's something somewhere that's a problem. So typical examples are campus firewalls, or, an early example I had was something plugged into a network port that was slower than you thought. So you've got a 100 megabit bottleneck on a network that otherwise 100 is gigabit, and that was 10, 15 years ago, so it's now gigabit rather than 10 gigabit. But a much more difficult to trace example we had some time ago was data transfers from the US to Queen's University Belfast. And they were having issues, and perfSONAR identified that sometimes the performance was pretty good, and sometimes it was abysmal. And it got, the periods when it was abysmal got worse and worse and worse. And it turned out that one of the 6 lasers in a link aggregation was a bit iffy. And once that was replaced, bliss, it got an enormous amount better. So I've talked about bandwidth, but latency is another thing that is of real interest. The latency from London to Vienna is around 30 milliseconds. The latency from a conductor to the back of an orchestra with the speed of sound at 300 odd meters per second is again 30 milliseconds. So in principle, musicians can play music together. And there's an example there where musicians are playing, I think, between 3 European cities. So you need a nicely tuned network. We've got a nicely tuned network. You need software that is appropriate and has low latency. And Géant, who link the European equivalents of JISC, have a map of the latency of their links. So that sounds wonderfully and easy, but we've been talking to a musician who wants to play, who did a test between London and Bristol. Now, the network latency between London and Bristol ought to be about 3 milliseconds. Apparently, he observed about 300 milliseconds. And so that's clearly a little bit of a problem. Now, we haven't investigated that in detail, but the usual suspect to blame is a corporate firewall, and probably a cheap corporate firewall that adds some significant amounts of latency. And so it'd be really nice to get that working for them. So one-way latency, which perfSONAR can measure. The other thing you can measure is performance problems before they become a performance problem. So you can measure buffers filling and congestion, even before you get packet loss. You can pick out asymmetric routes, but to do that, you need to have an accurate clock, and you want, therefore, hardware timestamping. So our counterparts in Ireland, HEANet, are particularly interested in precise time, and so we set up a little mesh with them. And in the top, you can see we've got reasonably steady latency, but you see some latency spikes, and those imply that some queuing somewhere on the path between us and them, or actually, I suspect, in their virtualization platform. On the bottom, I've got the latency between between Slough and this host, one of the hosts in Ireland, and one of the traces. So the red trace, I think, is IPv6, and the blue trace is IPv4, or maybe it's the other way around. But you can see that there's a really significant difference between those two. And on looking at it, it turns out we pair resiliently with them, and IPv4 is going over one routing, and IPv6 is going over the other. Not quite sure why. We did investigate and did get an explanation. But that's another thing you can measure. We're measuring latency from London to Slough, and you can see one direction on the left and one direction on the right. And what you can see is, although the underlying latency ought to be the same, you can see some significant latency spikes. And that, again, will be due to buffers filling up somewhere in the middle. And that's probably our 100 gig host testing at 100 gig and filling the buffers somewhere on the route. Now, one of the things that stymies us a little bit is clock drift. Now, you can see On the left, I think it's from London to Slough, and on the right, it's Slough to London for about 6 hours. And clearly, Slough is not getting, the fibres are not stretching asymmetrically enough that Slough to London is closer than London to Slough. So, I mean, it's only, half a millisecond difference between them, but it's quite significant. So it's clearly due to clock offset, and this is a clock close to our offices in Bristol, actually, which has got 2-minute hands. One for Greenwich Mean Time, and the other for Bristol Mean Time, separated by about 10 minutes. And it was necessary for the trains. So, you need to make sure you've got a stable clock. If you've got clock offset, clearly you can understand you've got a problem. Many modern network cards actually allow you to do hardware timestamping of network packets. And you can check whether they do with this ethtool command, so ethtool -t and then the name of the network card. And it'll tell you if it's got hardware transmit and receive timestamping. And to enable it, you just need to do HW timestamp star in your CronyConf, assuming you're using Crony. Quite why it's not the default, goodness knows. But if you're interested in precise timing, it's well worth thinking about doing that. So the other thing we're using perfSONAR for is to check the network parameter tuning, so we can advise people on what the best network parameters tuning for. So things like congestion control algorithms. We've been doing some tests on BBR3 and tests on MTU. The Janet network, like most other NREN networks, is capable of supporting an MTU of 9,000. And there's a lot of discussion about whether it makes any difference or not. And we've done some tests on that. Now you can do tests. So this is a test of cubic versus BBR. And I apologise, it's rather small. I should give credit to my colleague who created the slides that I've pinched a lot of, and apologise for the fact that this is a bit small. But we get significantly better performance with BBR using the test that you can see at the top, or perhaps can't see at the top, but you can run an individual test. The other thing you can do is to just change the parameters for the whole set of tests. And you can see here, the performance is pretty steady, and then there's a sudden drop. And that is due to us changing the MTU for the tests between London and Brookhaven, as it happens in this case. So Brookhaven's in New York, or near New York. So what we found is that for tests between our SURF in the Netherlands and Brazil, one of my colleagues was involved in doing some network tests. With jumbo frames, you got 31 gigabits. With the standard 1500 MTU, you got 20 gigabits. And similarly between London and New York, and between the Netherlands and New York. Now, this is just an artificial iPerf test. Results for your favourite data transfer mechanism may differ, but there's clearly a certain amount of potential there. And as I think I mentioned earlier, one of the big issues right at the top end is kernel performance and just shifting the number of packets. So bigger packets are easier to shift. We've moved to a new Grafana-based mesh, which has caused a little bit of disruption, but is clearly more sustainable. And we're supporting communities such as the Square Kilometre Array, Vera Rubin, which is a telescope in South America. And we're looking at a mobile thing on a small form factor PC or a Raspberry Pi. A number of educational institutes, so small colleges, are moving from gigabit to 10 gigabit connectivity, and they say, we've paid for a 10 gig, can you demonstrate it's really working? Because we can't. And they're keen to test it. So that's one of the things we're doing. And we're testing time, where we've got an interest in transferring time accurately, and our colleagues in Ireland are particularly interested in that. So it's a really interesting tool. It's all open source, and it's really useful for testing cross-domain. That's to say, testing between the two endpoints. And so you're potentially crossing the universe, you're crossing JISC, you're potentially crossing Géant and another university at the and NREN at the far end. And if you've got perfSONAR demonstrating you've got a problem, you can perhaps convince people that they need to look at it. And you've got the, if something suddenly changes, again, you can see that that a problem has occurred. And it's also been invaluable for testing network performance tuning. So there's a link there. The developers, like all open source developers, have got copious free time to do development and don't want any help. So if you are interested in it, they are really quite engaged, actually, and would no doubt welcome other users. It's available for Debian, it's available for Enterprise Linux, it's available for Ubuntu. And that, I think, is it from me. Any questions?
So I've seen scientific software and software done by serious people for serious jobs. Sometimes it can be a bit difficult to get to grips with. Can I use this to figure out which bits of my Wi-Fi are working? Or am I just going to have a really bad time with that?
So it might be a bit heavyweight. So it depends. I mean, the real benefit of this is it is essentially runs iPerf, and it runs it every 6 hours or at a time of your convenience. So if you're doing just from A to B, then it may be just as easy not to. But I mean, it's not. So, and I have to confess, I installed this and ran it 10 years ago. And it's my colleague who's done an awful lot of the work here. So it has been a bit finickety and has suffered from memory leaks, but we believe that those have now been fixed. So I don't think it's that difficult to install.
But it's mostly useful for ongoing monitoring.
It's particularly ongoing monitoring. I mean, there is another interesting use case, actually. So Rutherford have got 100-odd disk servers, and they wanted to say, oh, well, can we, as we commission the new disk servers, can we test against them? And of course, you don't want to run a script that runs a cron job against all of them, because they'll clash with each other. So there is the potential, actually, to run it in a mode that it instigates tests and one of the key things it does is it schedules the tests so they don't clash with each other. And so it could schedule the test against 100 different nodes in sequence. So, I mean, you could certainly use it, and I don't think it would be a bad thing to use. It produces the graphs, and it might be a little bit heavyweight, but it's worth having a look at, I think.
Thank you.
So RIPE has this concept of probes that can be installed all around to measure latency between them. Do you think this project could be integrated in a way so that rather than only focusing on latency, you could also look at bandwidth and so on?
That's a very good question, and the RIPE Atlas probes have got a slightly more extensively distributed, and indeed I probably should have mentioned them actually. The thing that the RIPE Atlas probes don't do is monitor bandwidth, and for big science experiments where you're transferring a lot of data, the ability to test and measure bandwidth is really quite important. So that's a lot of the thrust of perfSONAR, to actually do that measuring of performance. And I think the latency, the RIPE Atlas is designed for a small, cheap piece of hardware that you can put somewhere. perfSONAR, if you want to test data transfers from a disk server, you want sort of vaguely similar hardware. So, they're aimed at different sectors of the market, but I do wonder whether having perfSONAR nodes being able to act as a RIPE Atlas anchor might be an interesting concept. It can run in a container, so actually intrinsically there's no reason you couldn't have a node that is running a RIPE Atlas anchor in one container and perfSONAR in another. If you do run it in a container, you need to make sure you're running it in such a way that it binds tightly to the network card. Otherwise, you won't get particularly good performance. And if you're aiming to test network performance, you want to make sure you've got pretty good network performance. Ideally, by the way, you use two network cards, one for bandwidth and one for latency. So, Nick.
Hi. Have you explored user space TCP stacks, avoiding the kernel entirely? Things like Open Onload or DPDK?
No, is the short answer. No, I don't think so. The aim of this is really, and so particularly our interest in this is to provide a standard candle to demonstrate how is the network performing, how can we change things to make the network perform better, can we highlight network problems, and we participate in the mesh to provide a point in the middle, in a sense, to demonstrate that transfers between Lancaster and Rutherford, or Queen Mary and Rutherford, or Queen Mary and Brookhaven, if there's a problem, if they're getting decent performance, then that's great. If they're not, where's the problem, and can we try and trace it? And actually having a pair of nodes has been really useful for that sort of thing. So there is potentially work to be done in playing with that sort of thing, and if other people have done it and demonstrated decent performance. I went to a talk yesterday actually where the ESNet organised, and they were getting significantly better performance with later kernels, and they were tuning various things, and zero copy, for example, was one of the things that really appears to make a difference. So, yeah.
That was my next question. Was you talked about precision time protocol?
Yep.
At what point do you start measuring latencies on, I don't know, switching containers, or fractional differences between operating systems at both ends?
In terms of network performance, or in terms of time?
In terms of network performance and your monitoring, effectively.
So at the moment, as I showed, I think what we're measuring is clock drift. But I did a back of the envelope calculation, and being a physicist, there are 10 bytes in 10 bits in a byte, but you're all a little bit more sophisticated than that. So if you considered a 1250 byte packet, so 1250 byte packet is 10,000 bits. So the packet quantization time at 10 gigabits is 1 microsecond, or at 100 gigabits is 0.1 microsecond. So in order to measure accurately to measure packet delays, you want to get some fraction of that. Now, it depends how big your buffers are and how concerned you are about filling them. And indeed, so we're not yet at the level where I think we can say where we can measure that, but that's due to our clocks. So if you've got much more precise measurements of time, then I suspect that you might be able to get down to that level. The other point to make is that the current the current measurements are only based on software clocks. So they're essentially doing the one-way ping measurements are not using the hardware timestamping capability of network cards. It is being discussed doing that. But then, until that's been done, I think you're limited by the time it takes a packet to go from the kernel through to the network card, sit in the network card's buffers, and go out. What hardware timestamping on a network card does is it tells you exactly the time that a packet has gone out, or you can, in some circumstances, I think, set the time that a packet goes out. Now, so PTP relies on that. And just as a by the by, I think NTP is intrinsically as accurate as PTP. The thing that PTP gives you is that the intermediate network devices, so your switches and routers, if they support PTP, can tell the packet how much it's been delayed. And unless you have that, if you're going over several network segments, you're going to suffer from jitter there. But that's getting down to the microsecond levels of accuracy, if you are interested. And I can... There.
Another question. You said something about the throughput, etc.
Yes.
But the value is then disturbed if someone actually sends data, so you really need empty connections in order to have an actual throughput performance measurement?
Well, I mean, I think that's some of what that I suspect is so we're measuring performance, and indeed, if somebody else is trying to fill the network, then the performance we measure, because TCP gives you a level of fairness, the performance we measure will be reduced. So, and the latency, what you can also measure potentially is the latency increasing. So if you see that the latency is consistently high, you can demonstrate that the network is approaching full. But yeah, I mean, fundamentally, you can only get 10 gigabits down a 10 gigabit connection. So if you're trying to test at 10 gigabit and somebody else is transferring data at 5, then you'll see only 5. But I don't think that eliminates the utility of it. I mean, it's, you saw one of the examples I gave, there was quite a dramatic difference in performance one way and the other. And often for research data transfers, it's very spiky. I mean, if you look at universities' traffic, you've got sort of day-night, roughly sinusoidal periods, slightly less at the weekends. If you look at science traffic, it's either filling the link or, there's relatively little. So that's, I don't think that's intrinsically a problem, but.
Anybody else? Anyone? In that case, Chris, thank you very, very much for a wonderful talk.